చెప్పమ్మా. మ్యూటా? రైట్. Good afternoon, everybody. Welcome to online GATE classes in civil engineering, particularly concrete structures subject. In the last class, we have seen complete detailed discussion on outline of the concrete structures and working stress method of design. The various basic concepts that you have seen in the last class. And now let us have a review, and then we'll move to the solving numerical problems in working stress method of design. In the last class, overall outcome of it will be 3 different types of sections may be possible in the design of working stress method. It may be balanced section, it may be under reinforced section, or over reinforced section. So first you need to identify the type of section that the structure that the section will fall. If it is balanced section, the various constants are important, and already in the last class we have derived all the constants, and you know that m is modular ratio and k is neutral axis constant, x is equal to kd. In that k equal to 1 by 1 plus sigma st by m sigma cbc. So neutral axis constant, and j lever arm constant, z is equal to jd. So j is called lever arm constant, and r is moment of resistance constant. So these constants are useful if the section is balanced, or if you want to compare with the different types of sections, we need to compute the value of k, because xc will be equal to kd. xc will be equal to kd. So depth of the neutral axis xc, or depth of the critical section xc, is equal to k into d. So you need to compute the value of k and multiply by d, so that is xc. And if it is balanced, and you can use these appropriate formulas. So don't try to remember any of the formula here. Automatically these should be in your mind. And you know that it is simply singly reinforced section where the reinforcement is provided only on the tension face. And B is the width of the section, capital D overall depth, small d effective depth, x is the depth of the neutral axis, and d minus x is the distance of the steel reinforcement from the neutral axis. And 2 different forces are acting. One is compressive force by means of the compressive resistance of concrete, and the tensile force which is from the resistance from the steel reinforcement. And both C and T are equal at any stage. And initially, for analyzing the problem, you need to find out the actual depth of the neutral axis. If you want to find the actual depth of the neutral axis, what you do is take moments of all areas above the neutral axis and below the neutral axis, about the neutral axis. So area above the neutral axis is b into x. You can look at red hatched is b into x multiplied by x by 2 will be equal to equivalent steel area is m into ast, and its distance will be d minus x. So use this formula and compute the value of x. Once x value is known and already critical depth of the neutral axis is known, now compare it. If x is less than xc, then it is called the under reinforced section. Once it is under reinforced section, moment of resistance is governed by the steel reinforcement. So what is the moment of resistance? T multiplied by Z. So Z is the distance between the 2 forces. T multiplied by Z. What is T? Sigma st, ast. Z is d minus x by 3. So use this formula and compute moment of resistance. Or otherwise, if x is greater than xc, x is greater than xc, then this is called the over-reinforced section. Once it is over-reinforced section, moment of resistance is governed by the concrete. So C multiplied by Z. What is C? C is nothing but half into sigma CBC into B into X. That is simply average stress. Average stress is 0 and at the top it is sigma CBC, 0 plus sigma CBC by 2 multiplied by the area of concrete. That is called the compressive force multiplied by lever arm D minus X by 3. That's all. So the problems associated with this working stress method fundamental concepts is it may be any constant computation, or it may be a question only for finding the depth of the neutral axis for a given data, or the question may be when it is under reinforced, what is the moment carrying capacity of the section, or when it is over reinforced section, what is the moment carrying capacity of the section, and the last one is stress. So sometimes if the stress in concrete is known sigma CBA, you can call it as sigma CBA, actual compressive stress in bending in concrete. And you can find out the stress in steel by using this expression. So already I told you in the last class, these are the various related equations in working stress method of design. So don't try to by heart these formulas, always try to understand the whole concept with these set of figures. So with this we can switch over to numerical problems in working stress method. Let us go. Let us see a few problems on this by covering all these types of aspects. So already in the last class, it is clearly covered how to calculate the constants for balanced section. Now let us see, one problem is for computing the moment of resistance, another one is moment of resistance for over reinforced, third one is moment of resistance, computation of the stress in steel when the stress in concrete is known, and another problem is calculation of the AST for balanced section. So with this, all the types of problems will be covered in the working stress method of design. Let us look now. A reinforced concrete rectangular beam of size 250 mm, P250 mm, and effective, sorry, here it's missing, 250 by 500 mm effective, 500 mm effective, is reinforced with 3 bars of 20 mm diameter on tension phase. You can see the diagram, 3 bars of 20 mm on tension phase, and width is 250, effective depth is 500 millimeters. M20 grade of concrete. M20 grade of concrete means where FCK is 20 and sigma CBC will be 7, M20. And 415 grade steel. Steel 415 means Fy is 415, and stress in steel, because by using factor of safety, permissible stress in steel is 230 Newton per mm square. And accordingly, modular ratio, 280 by 3 sigma CBC, and for M20 grade of concrete, you will get 13. So what is the step in this problem? What is the question? Grade of is the moment of resistance of the section using working stress method is. If you want to calculate the moment of resistance, first you need to know which type of section it is, whether it is balanced section, under reinforced section, or over reinforced section. So for that, first to find out the actual depth of the neutral axis. Actual depth of the neutral axis. So for actual depth of the neutral axis, what we do? We are going to take the moments about the, neutral axis, moments of all forces above and below about the neutral axis. So what is that? B into x by 2 equal to m into AST into d minus x. Already you have seen. So here substitute the various values. Only unknown value is x. AST is known, D is known, everything is known except X value. So by solving this, you can get the XC equal to 177.7 millimeters. Sometimes in the examination, the question may be limited to computation of actual depth of the neutral axis. Or sometimes the question may be in the options, the given section is A, balancer section, B, under reinforced section, C, over reinforced section, D, data insufficient. So like that questions may be asked. If this is the question and to know the value of type of section, find out the critical depth of the neutral axis. XC equal to KD and K value you can find out using the standard formula, and ultimately XC is 141. So actual depth is 177, whereas critical depth is 141. So X value is more than XC. Here X value is more than XC, then it is called the over reinforced section. Over reinforced section. And once it is over reinforced section, the moment of resistance is governed by the concrete. That is half into sigma CBC Bx d minus x by 3. Just now we have seen this particular formula. And after substitution of all these values, you will get moment of resistance will be equal to 68.53 kilonewtons. So what is the procedure overall? First find out X value, and here X is greater than XC, then it is nothing but over reinforced section. Then moment of resistance will be equal to C multiplied by Z. Then substitute appropriate values and get the moment of resistance of the section. Okay. Now let's go for another problem. A reinforced concrete rectangular beam of size 250 mm by 500 mm effective is reinforced with 2 bars of 16 mm dia on tension face at the bottom. So the diagram it is given that width is 250 and steel reinforcement is 2 bars of 16 mm dia and effective depth will be equal to 500 millimeters. So this is the diagram given. If M20 grade of concrete and M20 grade of concrete means FCK20 and sigma CBC 7. And steel reinforcement 415, Fy is 415, sigma ST is 230. The moment of resistance of the section using working stress method is. So what is the moment of resistance? So the same procedure is being now applied. First what you do? You need to find out the actual depth of the neutral axis. First you identify to which type of section it falls. So for that, compute the actual depth of the neutral axis using the same formula discussed earlier, and by substituting the appropriate values, you will get the X value equal to 125.2. And in the same way, because here both for all the problems I took only M20 grade and Fe415, 250, 500. Because you can compare and you can understood how it is changing from under reinforced to over or over to under reinforced type of section. So once you got the X value, so in the similar way of it, X is equal to KD and accordingly find out the XC. Compare these two values. Now X is less than XC. Actual depth of the neutral axis is less than the critical depth. Then the section is called under reinforced section. And moment of resistance will be governed by the steel reinforcement. So sigma ST, AST, D minus X by 3. Substitute the appropriate values and this will be the final value. And here you will get the magnitude 42.4 into 10 power 6 Newton millimeter, because all the values substituted here are in newtons and millimeters. It will be multiplied by 10 power 6 and finally in kilonewton meter 42.4. So here the questions in the examination may be what is the depth of the neutral axis? That may be the question in the exam. Or the second question may be the type of section is. What is the type of section here? It is called the under reinforced section. Sometimes the question in the examination, one of the option is under reinforced. And another question for the same problem may be what is the moment of resistance of the section? What is the moment of resistance? Sometimes fourth problem may be the question. What is the fourth problem? If this section, if this section is used as a simply supported beam of length L and concentrated load W, what is the magnitude of W? What is the safe value of W? So in this case, what you do? Moment of resistance will be equal to bending moment. What is moment of resistance here? 42.4 kilonewton meter will be equal to W into L by 4. You know WL by 4 is bending moment. And if the span is known, you can compute the magnitude of the load also. So sometimes if the examiner wants to give a little bit tough question, and naturally the extension may be like this. So what is the magnitude of the safe load that the simply supported beam can carry? Maybe the question. So that is another question will be what is the concentrated load? Or sometimes the beam may be with uniformly distributed load. If the beam is with uniformly distributed load, M will be equal to WL square by 8. And you can find out another question is what is small w. So in this problem, several questions may be in the examination. If the examiner wants to give a simple question, he will ask only x value. What is x value? What is the depth of the neutral axis? And if you want to test some other thing, he will ask what is the type of section. Or a bit tough means moment of resistance. A little bit extension means what is the safe uniformly, what is the safe concentrated load acting on the beam. Or it may be what is the safe uniformly distributed load that the beam can carry. So like that small questions will be posed on this. So that means this question can be composed of several questions in the examination. Third one. So that means under reinforced is over. Over reinforced moment carrying capacity is over. Now let us see if a question for balanced section. A reinforced concrete beam of rectangular size 250 by 500 mm effective. So here also the same size 250 by 500 millimeters. It is 250, effective is 500 mm. Is designed using M20 grade of concrete and Fe415 grade steel reinforcements. The constants for balanced section are using working stress method. The area of steel reinforcement required for balanced section is. So here the question is how much is the quantity of steel reinforcement corresponding to the balanced section? How much is the corresponding quantity of steel reinforcement required for the balanced section? You know, at the balanced section, the moment of resistance is governed by both concrete and also steel. Both concrete and also steel. So moment of resistance is either C into Z or T into Z. T into Z or C into Z. So you know that particular formula, moment of resistance will be RBD square. Moment of resistance is RBD square, that you know. And R value is given in the question. So RBD square equal to what is moment of resistance because of tension? Sigma ST, AST, JD. So you know that when it is for balanced section, lever arm is equal to JD. Lever arm is equal to JD. For other two cases, lever arm is D minus X by 3. So here substitute J and D and get the value of AST. That's all. So or otherwise also you can do, because in the moment of resistance both Z values are same. You can look at C into Z will be equal to T into Z in this formula, C into Z, T into Z. So Z gets cancelled. What is the remaining? C equal to T. So sometimes you can also use C equal to T. What is C? C is nothing but half into sigma CBC into B into XC, because here the depth of the neutral axis is now XC, will be equal to sigma ST multiplied by AST. You can also use this formula and compute the value of AST. It will be the same value, 539.9 millimeters square. And what is XC? XC is nothing but KD. K value is given 0.283. So substitute XC by 0.283 times of D. And everything is known. You need not go for even R value, J value, not required also. Because moment of resistance is governed by both concrete and steel. And at that time, both steel and concrete reaches its permissible values. So C is equal to T, and accordingly you can use this formula for computing the area of the steel reinforcement. So in this way you can also do it. And sometimes if to the extension of this, the question may be how many number of 16 mm dia bars required. 16 mm dia, how many number required for it? That may be sometimes question. So how do you get number of bars? Number of bars will be AST divided by area of each bar. What is the area of each bar? It is nothing but 539.9 divided by area of each 16 mm dia bar is something like this. It is just 2 point something. So the number of bars required will be 3. So the question need not be only the magnitude of area of the steel reinforcement. It may be extended how many number of bars are required. You will get here 2 point something, and the number of bars required for this particular section will be equal to 3 numbers. So this is how the problems are to be solved. The next one. You can see the question look like very big when compared to the previous one. When the question is big, solution is simple normally. A reinforced concrete beam of size 250 by 500 mm effective, you can look at the diagram, is reinforced with steel reinforcement, some steel reinforcement on tension phase, such that the compressive stress induced on the extreme compression fiber is 7 Newton per mm square. You can look at here, some reinforcement is provided at the tension phase, and because of that steel reinforcement, the stress induced at the compression phase in concrete 7 Newton per mm square. The position of the neutral axis lies at 180 mm from the compression phase. It is also given. Position of neutral axis is also given. If M20 grade of concrete and Fe 415 grade steel reinforcement is used for design, the tensile stress induced in the steel reinforcement. So what is the amount of steel reinforcement in the amount of stress induced in the steel? So everything is known. You know this equation just now we had completed discussion about it. Sigma ST, remember that. Just try to understand this diagram. From this you can write the equation sigma ST divided by sigma ST divided by M, because it is equivalent concrete, and this is divided by what is that value? D minus X will be equal to sigma CBC divided by its associated value X. So from this you can develop this particular equation. No need of remembering any particular equation. So from this sigma ST is M sigma CBA T minus X by X. So here actual stress sigma CBA, compressive stress in bending, actual compressive bending stress in concrete, and sigma STA, actual stress in steel reinforcement. So it is 161.8 Newton per mm square. Or sometimes if sigma ST given, you can find out what is sigma CBA. What is sigma CBA? So that's all about the various types of problems that are associated with the working stress method of design. Now let us move to limit state method of design. Limit state method of design. So which is most important, and all rest of the topics are basing on the limit state method of design. So working stress method concepts, fundamental concepts only included in the syllabus, whereas in case of topics on limit state method, it will be up to the end of all the chapters. Okay, it consists of all the chapters. Of course, when certain cases only fundamentals in those are required. Particularly, majority of the questions in the examination are based on the concepts of the limit state method of design, particularly singly reinforced and doubly reinforced T-beams. And beyond that, some questions may be on shear, torsion, very few questions may be bond and other columns, etc. So those things will be nothing. Only the fundamental concepts are more important, and it is more tough at the fundamental stage. And I will try to make this very simple understanding concepts in the limit state method of design. So now already you have seen two different methods in the last class: working stress method of design and ultimate method of design. Normally why design requires, because the structure is composed of several members, and it is made of concrete and steel, and it has to transfer the loads effectively that are coming on the various elements. So the loads must transfer from superstructure to substructure and substructure to the underneath the soil without any difficulty, and at every stage each and every element in a structure or a structure as a whole must be safe, and it should serve for the its intended purpose. So here the materials that are being used for any structure uncertainty. So because of uncertainty in both material strengths and also loading, so we need to consider or we need to impose the factor of safety effectively, so that the structure is safe and it should serve for the purpose. Whereas in the previous methods of analysis, for working stress method of analysis, the safety will be provided for the materials by reducing the stresses, using the factor of safety. And whereas in case of ultimate method, load factor will be used for introduction of the factor of safety in the ultimate method. And however, there are so many theoretical problems, and there is no exact justification for the use of factor of safety only for materials and only for the loads in working stress and ultimate load methods respectively, and those methods are now outdated. And now to overcome all the drawbacks and difficulties that are there in working stress method of design and limit state method of design, a new approach has been given, that is based on the reliability concepts, reliability analysis performed by introducing factors of safety for both loading and also materials. Because for any structure, one is materials that are to be used for construction of the structure, another one is the loads that are acting on the structure. So these are the two main components, and these two are having lot of uncertainties. So we need to introduce factor of safety for both loading and also the material strengths. The factors of safety considered in both the material and loading. That's why it is materials and also material strengths and also the loading. Then it is these factors are called the partial safety factors. Partial safety factors. Limit state method provides adequate safety at ultimate loads because we are providing a factor of safety for the load, and also adequate serviceability at service loads because factor of safety is also induced by limiting the stresses. And the limit state method is completely basing on the probabilistic approach. Probabilistic approach. And the factor of safety for loads and material strengths are determined based on the probabilistic approach only. And in the limit state method of design, the very basic concept is that the structure shall be designed to withstand safely all loads liable to act on it throughout its life. So during the entire life of the structure, whatever the loads that are coming on to this must be, the structure must be safe, and it shall also satisfy the serviceability requirements such as limitation on deflection and limitation on the width of the crack. So that means any structure that is designed based on the limit state concept must be safe throughout the life of the structure, and it should also serve the serviceability requirements. So that means the main criteria for the design of any structure is safety and also serviceability. So those two things are satisfied while for designing the any structure or members by means of limit state method of design. The acceptable limit for the safety and serviceability requirement before failure is called limit state. So at the time of failure, the acceptable limit for both serviceability and safety requirements just before the failure is called the limit state. The aim of the design is to achieve acceptable probabilities that the structure will not become unfit for the use for which it is intended. So that means the structure should be capable of resisting the loads till the collapse in condition. All the limit states shall be considered in the design to ensure an adequate degree of safety and serviceability. All limit state means there are several limit states already outlined. Now also we are going to discuss, that is limit state of collapse, limit state of serviceability, again in the limit state of services collapse and also limit state of serviceability. There are again several other limit states also there that will be discussed a little later. The structure shall be designed on the basis of most critical limit state and shall be checked for the other limit states. So normally any structure is to be designed for the most critical limit state means say for bending. For bending, the member is designed for bending, and again it will be checked for the other limit state. So it should be checked for serviceability requirements, whether the deflection of that particular member is within the limits or crack widths of the crack width that is developed in the structure is well within the limit or not. So that means the design is for the critical state and it should be checked for various other possible limit states that the structure concerned. And the design should be based on the characteristic values for material strengths and also the applied loads. So we have to find out the various characteristic loads and also characteristic strengths for both materials and also the loads. And already the design values are introduced through the use of partial factors of safety. And already I told you there are different types of limit states. One is limit state of collapse. So the structures will be designed, structure or element can be designed, element in a structure can be designed according to the type of force that is acting. It may be a flexure, compression, shear, torsion, or maybe a combination of all the different types of forces. So the limit state of collapse of a structure or part of structure could be assessed from the rupture of one or more critical section and from buckling due to elastic or plastic instability or overturning. So here assessment is till the failure of the structure or till the failure of the one or more critical parts of the structure. The resistance to bending, shear, torsion and axial loads at every section shall not be less than the appropriate value at that section produced by the probable most unfavorable combination of the loads. So that means at any stage, the resistance of the structural component, the resistance of the structural component must be greater than the most probable unfavorable condition of the loads acting on the structure. So that means if the structural member is designed for bending, and the member is having some flexural resistance, that resistance must always be more than the resistance due to loads because of all possible worst favorable and worst unfavorable combination of the loads. So that means the strength of the member must always be more than the movement, the forces that are induced on the structure. It shall satisfy the performance serviceability requirements such as discomfort caused by excessive deflection, crack width, leakage, loss of durability, etc. under service loads. So what is going to happen is sometimes because of the service loads, the deflection may be more excessive. If the deflection is excessive, then the purpose of the structure may not serve its intended purpose, or if there are some small cracks in particularly leakage structures where it is storing the water and other fluids, then it affects. And durability also to be considered another factor, another important factor. And excessive deflection normally reduces the efficiency of the structure, and all these other limit state must be well within the limits specified in the code. And other limit states. So any other limit state can be considered other than the two limit states given above. Any unforeseen or unusual special functions that are comply with any relevant additional limit states considered appropriate to that particular structure. When a structure has reached a limit state of serviceability, so normally what is going to happen when the sometimes when the moment of resistance of the section is same as that of bending moment induced on the structure, then that is at the verge of the failure. Then that is at the verge of failure. But that means the structure may reach its limit state in collapse, or the structure may reach its limit state in serviceability. So in normally what we do in the case of structure reaches its limit state of collapse, once it reaches the limit state of collapse, it does not recover to its original shape. So because of some loads, additional loads acting on the structure, if the structure reaches the limit state of collapse, even after removal of all the loads, it won't recover. It will not recover to its original shape. Whereas when the structure has reached limit state of serviceability, for example, the deflection, it reaches the deflection, maximum deflection specified in the code because of some load acting on the structure. And on removal of the load, the structure will recover to its original shape. The structure will recover to its original shape. So when a structure has reached the limit state of serviceability and on removal of loads, the structure will return to its original shape. Whereas when the structure reaches the limit state of collapse, it will not recover to its original shape. And limit state method of design aims for a comprehensive and rational solution to the design problem by considering safety at ultimate loads and serviceability at working loads. RCC members are not designed to resist direct tension. So RCC members are any other limit states mentioned in the limit state or otherwise even in limit state of collapse, only flexure, compression, etc. it will be given. This compression is particularly for the columns, and there is no tension here. There is no tension. It is here because of the flexure, tension may occur. That is flexural tension, and because of shear torsion, all those tension may occur. But even with the compression also, eccentric load applied, tensile stresses will induce in the structure. But for the direct tension, if any RCC member is subjected to direct tension, it is not included in the limit state of collapse. It is not included in the limit state of collapse, and axial tension is not considered in the limit state of collapse. Then before going for the probabilistic approach, let us see the grades of concrete and how the strength of the concrete and other small relative things. Only we are concentrating on the grades of concrete because different grades of concrete is being used, M20, 25, 30, etc. And what is grade and how these values are to be computed from the experimental results, etc. will be concentrating now. Different grades of concrete can be obtained by proper proportioning of the constituent materials. So, cement, fine aggregate, coarse aggregate, and if necessary, admixtures. By appropriate proportions, we can obtain the different grades of concrete. Compressive strength is the most important property for the concrete. Because several other properties of the concrete, just like tensile strength of the concrete, bond strength of the concrete, density of the concrete, impermeability of the concrete, and other related properties, all are related with the compressive strength of the concrete. If the compressive strength is more, then naturally other strength properties also will be more. And the compressive strength is related with the various other strength values. And normally compressive strength of concrete is obtained by applying compressive load on 150 mm cube specimen at 28 days after curing. So once the cubes are casted, 150 mm size of cubes are casted, and it will be kept for curing for 28 days, and the cubes are to be tested only after 28 days, immediately after 28 days. So cube is this is the size of the cube, and here pouring the concrete from the top, and sometimes what is going to happen is the top surface may not be perfectly leveled. When the top surface may not be perfectly leveled, and while testing, the compressive load should not be applied in this way. Compressive load should not be applied in the direction of the casting. So this is the direction of the casting, and because the top surface may not be smooth and the load may not transfer effectively for the entire 150 by 150 mm cross sectional area. So that's why the cubes are always tested other direction of the casting, other than the casting direction. Cube is always tested on sides only. That means cube testing direction must be other than the direction of casting. Now, test results of sample. So normally what we do, if you take only one cube and if you test it, that is not the compressive strength of the cube. So compressive strength of the cube must be average of the three specimens. It's a must. So for any particular concrete in the field, so the minimum three concrete specimens, three concrete cubes must be casted. And once these three are casted, find out the compressive strength of the individual cubes and then find out the average. So average of the average strength of the cube specimen is F1 plus F2 plus F3 divided by 3. But there are certain small conditions here whether the concrete is having average value correct or not. Have average value correct or not. So while computing the average compressive strength of three specimens, individual variation should not be more than 15% of the average. 15% of the average. For example, that means all the three specimens must give appropriately the results well within the 15% of the average. For example, if one cube is say 32, another cube is 31, one more cube is 30 Newton per mm square, you can take conveniently average of all the three specimens because naturally that will be well within the 15% of the average. But the same thing, if the values are one is say 32, another one 10, and one more is say 30. So we cannot call it as average compressive strength because 32 is all right, 30 is all right because these two cubes will give appropriately good strength, and whereas 10 means it is very low. It may be 10 or it may be even 70. Either lower value or higher value, but the deviation is large. When there is a deviation, large deviation that is more than or less than 15% of the average, then that results are not correct. So average values of the cube strength must be within 15% of the average results. If the individual variation of the compressive strength of the specimens is more than 15%, is more than plus or minus 15%. That means it may be less than 15%, or it may be more than 15% of the average. The test results are not valid. For example, if the values are 32, 31, 30, then you can consider the average value, that's all right. Because the variation is less than 15%. And in case of 32, 10 and 30, the variation is more than plus or minus 15%, then this results is not good, and average of all these three specimens is not correct, and some other method is to be evaluated for determining the strength of the concrete. Now let us take a small example. The three cubes are tested. One is 38, 30 and 37 Newton per mm square. What is the average strength, whether it is acceptable or not? Average strength is average of the 3 divided by 3. It will be 35 Newton per mm square. 35 Newton per mm square. And now whether this 35, because one is 38, another one is 30, one more 37, one is less, whether it is acceptable or not. Now what you do, you have to see, simply average itself is not the mean value of the compressive strength. You should also check whether the deviation is more than 15% or less than 15%. So what you do, if you want to check for percent variation for say 38, you can look at 38 minus average value divided by average, because the deviation is with respect to the average. In the previous line, you can look at here. You can look at here. Variation should not be more than 15% of the average. So the comparison is based on the average value. Comparison is based on the average value. So strength of first one cube, average value divided by average value into 100, it is 8.6. So similarly, find out the other one. Here what is the for 30? It is 30 minus 35 divided by 35 into 100. So this is some minus value, minus 14.3, and all these three are well within the limits. So variation is less than 15%. Less than 15%. So the average strength 35 Newton per mm square is correct. This is the exact procedure for computing the average. Now let us look another example. Tube strengths are one is 38, 28, 39. So these are the three different cubes, and similarly average value will be same as that of previous one, computation 35. Now look at the computation of variation. Say for 28 cube 28 minus 35 by 35 into 100, it is minus 20%. So here it is minus 20%, and of course other things may be less than 15%. Though two cubes are less than 15, that is immaterial. If any one of these values, any one of the variation of the tube strength is more than 15%, then the test results are not valid. So whatever the results you got, 38, 28, 39 are invalid. You cannot compute average of all the three. Whatever the results that you got from the tube test is not correct, it is false. Now, acceptance criteria. Acceptance criteria. So before going for this, we will go to some other thing. Okay, no problem, because you know certain things. Acceptance criteria. So whatever the compressive strength that you got from the results of the field, whether it is acceptable or not, that is to be observed now. For compressive strength, the concrete shall be deemed to complete with the strength requirements when both the following conditions are met. So that means when conditions A and B satisfies, then only the strength is accepted. Otherwise, the strength is not accepted. So here the specified grade M15, M25 or above, M20 and above, M20, 25, 30, anything. So here mean of the group of 4 non-overlapping consecutive test results. So in this particular case, the value must be more than FCK plus 0.825 times estimated standard deviation. So it is nothing but FCK plus 0.825 sigma. So FCK, characteristic strength of concrete, that we are going to discuss little later in detail, plus 0.825 times of sigma, or FCK plus 3 Newton per mm square, whichever is greater. For concrete of M15, this one. For concrete of M20 and above, FCK is same value and FCK plus 4 Newton per mm square, only the greater of these two. Consider the greater of these two. So that means the mean of the group of 4 non-overlapping consecutive test results must be having more strength than these values. So these are the reference values, and the cubes that are tested for characteristic strength must be more than this value, that we will see little later with the example also. And sometimes what is going to happen, few cubes may be giving more strength and 1 or 2 cubes may give less strength. So in such a case, the restriction is also given. So if the individual test results must be more than FCK minus 3 in case of FE M15 grade of concrete. For M20 and above, individual test results must be more than FCK minus 4. FCK is the characteristic strength of the concrete. Say for example, if it is M25, okay, if it is M25 FCK, 25 plus 0.825 into sigma. That is the minimum value. That is the minimum value. Or FCK plus 4 Newton per mm square. So this is the reference value. While for the cubes tested in the field, the strength must be more than this value. Then only it will be accepted. And also at the same time, the individual test results of the cube must be more than FCK minus 4. So I will read this. The mean strength determined from any group of 4 consecutive test results complies with the appropriate limits in column 2 of the table shown below. So that means these are the reference values, and the values of the compressive strength tested in the field must be more than these values. Second one, any individual test result complies with the appropriate results in column 3 of the table shown. So any individual results must be having the compressive strength more than FCK minus 4. So then only that particular grade of concrete is acceptable. Otherwise it is not acceptable. And normally for establishing the standard deviation, because this method, limit state method of design is statistical analysis and probabilistic approach is being used. For establishing the any value, say for example standard deviation, minimum of 30 samples should be considered. Then only you will get exact result of the standard deviation. And in the absence of test data, then these values are to be considered as standard deviation. For grades of concrete M10 and M15, 3.5 Newton per mm square, M20, 25, 4 Newton per mm square, and M30 and above 5 Newton per mm square. Sometimes this may be the question. The standard deviation, the standard deviation for M20 grade, 25 grade of concrete is, answer is 4 Newton per millimeter square, Newton per millimeter square. So just try to remember 3.5, 4 and 4.5. Here it is M20, 25 and the different grades. So first two are only for PCC, and minimum grade of concrete for RCC is M20. So M20 and M25 it is 4 Newton per mm square, and beyond that M30 and above 5 Newton per mm square. So in all these grades of concrete mix, M is refers to the mix, and the number indicated will be the characteristic strength of the concrete at 28 days. Characteristic compressive strength of the concrete at 28 days, and for getting the exact standard deviation, minimum of 30 samples should be considered for the statistical analysis. And that is regarding acceptance criteria for the compressive strength. Sometimes what we do, we test the members for flexural strength. When the flexural strength is being tested, so here also these two conditions should satisfy, then only the flexural strength obtained from the experiment is valid. Experiment or the results of the flexural strength values obtained from the laboratory or from the site are acceptable. Otherwise, these values are not acceptable. So, acceptable criteria for flexural strength is when both of the following conditions are met, the concrete complies with the specified flexural strength. The mean strength determined from any group of 4 consecutive test results exceeds specific characteristic strength by at least 0.3 Newton per mm square. The strength determined from any result is not less than specified characteristic strength less 0.3 Newton per mm square. So what is going to happen here? Flexural strength, say for example, FCR. Assume that for a particular concrete it is 2.8. It is only assumption, 28. And it is acceptable. For example, you know that for M25 grade of concrete, FCR will be equal to 0.7 times root of FCK. So that means it is 3.5 Newton per mm square. Let us assume that it is 3.5 for M25. Now whether it is acceptable or not means, for the structural members tested, the strength must be 3.5 plus 3. 3.5 plus 3. That means the members tested in the lab or field must be more than 3.8 Newton per mm square. Then only that is accepted for M25 flexural strength. And at the same time, individual members should not be less than the value minus 0.3. That means it is 3.5. Any individual test should not be less than, any individual result should not be less than 3.2. What is this 3.2? 3.5 minus 0.3, it is 3.2. So individual results must not less than 3.2 and average value must be more than 3.8 Newton per mm square. Then FCR 3.5 is acceptable and that is for M25 grade of concrete. Otherwise, it is not acceptable. Both the conditions must be satisfied. Now, variation of strength. So normally the statistical analysis is to be used for the analysis, and here what you do is frequency density. Frequency density means number of samples in an interval divided by total number of samples. So how much frequency the samples are to be tested will be obtained using this formula. So normally what is going to happen, since concrete is not homogeneous and the conditions are not ideal for preparation of concrete and also preparation of cubes, strength of the concrete varies in different testing. That means if you cast a cubes, 3 different cubes for a same concrete, one gives a strength of 32, another gives strength of 28, one more may give strength of 33. So that means the difference is preparation of the cubes, that means compaction, working, etc., and also variation of the properties of the concrete. Then because of non-homogeneity and rate of application of the load on the cube, etc., will affect, and the results may not be exact. All the three cubes may not give you the exact results. So that's why for getting the exact value, large number of samples are to be tested for exact computation. So the probability distribution curves will be obtained when a large number of samples are to be tested. When the large number of samples are tested, you can find out the histogram. You can find out the histogram. Histogram is nothing but it will be something like this. Say for example, this is one particular strength, this is another strength. Like that, when largest number of samples are to be tested, the results will come like this. When large number of samples are tested, the results will be coming like this. That means, for example, this is compressive strength of 25 Newton per mm square. So it may be 40 numbers. And another one is 24. It may be lesser, so 35. Like that it will be, and similarly 26 Newton per mm square. It may be 36. Like that, on the x-axis it is compressive strength, x-axis F compressive strength, and y-axis number of samples or frequency. You can call it as frequency. So that means 25 Newton per mm square, 40 numbers. 24 Newton per mm square, 35 numbers. 26 Newton per mm square, you will get 36 numbers. Like that, you can plot the histogram. So this is possible only when you test large number of cubes. If you test only very small in a number, you cannot the exact statistical results. So large numbers are required to get the probability density curve by means of the histogram. So what is going to happen if the numbers are less? If the numbers are less, you will get some histogram. If the numbers are more, what is going to happen will be, if you just join all the peak values, it will follow the curve. So what is this curve called? This curve is called the probability density curve. Probability density curve. So it is the line joining the points of all the peak values of the different magnitudes of the strength. For example, this particular concrete is average compressive strength is 25. But in the laboratory, if you test 100 cubes, all the 100 cubes are not 25. Some cubes may fail at very low stress. Some cubes may fail at very high stress. And the majority of the cubes will fail around 25 Newton per mm square. And if you plot a histogram by considering the large number of samples, if you join a smooth curve between the center of all these points of the histogram, this is called the probability distribution curve. And this curve is called the normal distribution curve. That curve is called the normal distribution curve, that we will see little later. The probability is symmetrical about mean. The probability distribution curve is called the normal probability curve. So this curve is normal probability curve, and it has some normal distribution equation. It follows normal distribution equation, and the total area of the normal distribution equal to 1, because the total area means the total probability of occurrence of all the strengths for average of M25 grade is within this particular limits. So area is only 1. So now let us look at here before going for that. Mean strength. If several values of the strengths are obtained, average will be equal to sum of all the strengths divided by the number of the samples. And n number of samples, f is the strength of the ith sample. Standard deviation, n is sigma equal to 1 by n sigma fi minus x bar fi. Fi means ith sample minus f bar whole square, and this formula is applicable n is greater than 30. And when number of samples are less than 30, and even for the examination purpose also, if at all numerical questions on this, number of samples may be 3 or 4 or 5, 6, not more than that. And always this formula is to be used for calculating any numerical value of the sigma in the examination. So sigma is sigma fi minus f bar, fi minus f bar whole square by n minus 1. So these are the formulas for computing the standard deviation for the samples more than 30 and also less than 30. And normally what is going to happen here, sigma is always measures the spread of the value. Spread of the value. For example, if the cube strength is 35, 35 and 35. Is there any spread of the deviation? No spread of the deviation. All the sigma value is equal to 0. Standard deviation equal to 0 because there is no deviation from the mean. What is mean? Here the mean is also 35. Is there any deviation of the sample from the mean? No. 35 minus 35 0, 35 minus 35 0, 35 minus 35 0. So there is no deviation. So here the particularly standard deviation fi minus f bar whole square, that means deviation of the sample from its mean is measured in standard deviation. So sigma is always measure the spread of the value. And it will say the quality, whether the values are well within the limits or a large deviation. And higher the value of sigma, more variation. Higher the value of sigma, because these results are with reference to the compressive strength. When higher the sigma value, more strength variation. More strength variation means one cube may be 35, another cube may be 25, one more cube may be 42. That means the variation of the strength is more, and hence it is called the poor quality control. Whereas if the lower value of sigma, that means variation or deviation is low, then it is less strength variation. Variation is less. When variation is less, it is an example of say 35, 33, 35, 33, 32. So the variation here is very less. Or if you consider this all the three, 35, 35, here in this particular case sigma itself is 0. There is no variation at all. That means the quality is very high. So when sigma is small, quality is very high. When the sigma is more, quality of the strength of the cubes is less. Now, sometimes what is going to happen is the frequency distribution. When the frequency distribution is known and you are familiar with x value, f values, so I am using like this because in the previous case directly I used f means mean strength and n means number of samples, etc. Here f refers to the mean strength, only one symbol. But normally for the frequency distribution, f is the symbol for frequency. And you are familiar with these equations. Let us have initially the mind only with the existing knowledge. Average value will be sum of the product of Fi into Xi. Fi into Xi. That means how many number of samples multiplied by its strength divided by total number of samples. Sigma Fi is nothing but n, total number of samples. And computation of sigma is 1 by n minus 1, the same thing. In the previous case, sigma is nothing but 1 by n minus 1 Fi minus F bar whole square. So, but here frequency is introduced. So, Fi multiplied by Xi minus X bar whole square. And you are familiar with all these things. It is a statistical question studied at lower standard. And sigma Fi is the total frequency, which is called n. So, normally here what you do is X means strength of ith specimen. Xi. What you do? Xi means strength of the ith specimen. Fi means frequency of ith specimen. That means how many number of specimens with the strength of Xi. Fi means F1 means how many number of samples with X1 strength of the cube. Like that, it will be used for computing the frequency distribution, computing X bar and also sigma for the frequency distribution. Now, it is already you have seen the histogram and line joining the points of all the peak values will form a normal distribution curve like this. So now it is normal distribution curve. So here the probability. So this is called the probability on y-axis. It is probability density function. So write small p, probability density function. And x-axis f. F means strength of the sample. Strength of the sample. F bar means average of all the samples. So that means average of the sample F bar is here, and deviation towards right, deviation towards left occurs in this particular diagram. And exactly at the center, you will get the average value of the samples. Average value of the samples. And normal distribution curve, probability density function, or probability density function or frequency density curve is represented by sigma and mu square. So this is always represented by sigma, standard deviation, and mu is the average value. Sometimes what we do is, in place of F bar, we write mu. Mu is the mean of the normal distribution. Mean of the normal distribution, which is the exactly at the middle. So from this particular equation, F of sigma mu square equal to 1 by sigma root 2 pi e power minus half x minus mu by sigma whole square. So this is also useful in mathematics, normal distribution curves, probability chapter. It will also be there. Okay. So this is the original function. This is the original function given. But according to our requirement, this F is nothing but P, probability. We can call it as probability density, and 1 by sigma root 5. And here X. In place of X, now we are using F, strength of the cube. And another one is X mu. In place of mu, we are using F bar, because these are the symbols that we are using. Let us change the values now. Divided by sigma is the standard deviation. So you can use this particular equation for it. Okay. So now you can write on x-axis F, y-axis small p probability, and it follows the bell-shaped curve. Bell-shaped curve. And another term is standard normal variate. Z is standard normal variate. F minus F bar by sigma. F minus F bar by sigma is the normal variate. And here the area is more important to compute any value, and accordingly the tables are given corresponding to the normal standard variate. So for analyzing this type of problems, we need normal distribution tables. We need normal distribution tables. So normal distribution tables are useful for analyzing this particular problems. So now let us look at our topic. So here this is 0. The 0 means here there is sigma. You can call it as what is the variation at this point? At the exact point, at the exact middle, the sigma value is equal to 0. At the middle, sigma value is equal to 0. There is no variation because all these samples are about the mean. What is the deviation? You know, the deviation is nothing but sigma is nothing but f minus f bar by something. Here f is f bar also f bar, so f bar minus f bar will be equal to 0. So that means exactly at the center, standard deviation sigma equal to 0. And at to the left you can call it as minus sigma. You can call it as minus 2 sigma. You can call minus 3 sigma. And similarly on the right side, plus sigma, plus 2 sigma, plus 3 sigma, and so on. So that means, if for example, if you want to calculate any value at this particular point, what is the value of the f here? Let us call here f1. How to calculate that f1 value? F1 value is nothing but f bar. You know that it is f bar plus k times of sigma. If sigma is say 2 sigma, let us call, if you want to calculate the value corresponding to 2 sigma, what you do? K is equal to 2. So that means f bar plus 2 times of sigma. That means the ordinate, the value of the stress, this value, the value of the stress at this point is f1. That value is obtained as f bar plus k times sigma is the generalized term, and k here, if you want 2 sigma, f bar plus 2 sigma. And knowing the average value and also sigma from the previous things, you know, here from the previous things, you know, x bar and also sigma, by knowing all these values, you can compute what is the magnitude of the stress at a deviation of plus 2 sigma. So this is how some small numerical problems associated with this. Now, let us look at the area of probability density for curve is 1. So this entire area, the total area of the curve with the x-axis will be exactly equal to 1. And these are the standard values. Obtained from the statistical tables. P, probability of mu minus 1. That means probability of variable x is mu minus sigma to mu plus sigma is 68.26. The meaning of it will be, you can look at it as mu means f bar, but because you are familiar with the statistical things, let us go first with this, then you can move. This is the mu value at the center. Mu minus sigma means this is the point. This is the point of mu minus sigma. And this is the point of mu plus sigma. So that means probability of x varying from mu minus sigma to mu plus sigma is 0.6826. It is from the statistical table. That means the area of the hatched portion is 68.26. What is total area? 100% or 1. When the total area is 1, this contribution is 0.6826. Similarly, Here 2 sigma and 2 sigma. If the area in between the mu minus sigma to mu plus 2 sigma, the total area will becomes 95.44%. And if you go for three times of the variable, mu minus, this point is nothing but mu minus 3 sigma. This point is mu plus 3 sigma. In that, the area covered will be 99.73 and a very small value on the other side. Okay, so sometimes in the examination in mathematics or in structural design subject, this may be the question. So what is the meaning of it here? If you look at the top one, you can observe here, it is nothing but 0.3413. That means this hatched portion area is 34.13% or 0.3413. You know, it is on either side it is 0.6826. Only on one side, what is that value? 0.3413. 0.3413. So that means here you can look at probability of x is between mu and mu plus sigma. You know, here it is mu and this is mu plus sigma. It is mu and here it is mu plus sigma. The area lying between these two is half of this. Is half of this total area. Half of the first one, 68.26%, now 34.13. And similarly, from mu to 2 sigma, it is 0.4772, half of this. Similarly, the other half. So this will be useful for computing the probability of the probability of occurrence of the cube strength values. Probability of occurrence of the cube strength values. Particularly from this different types of questions, sometimes what is going to happen is, the question is, what is the probability, what is the probability that the compressive strength attains mu plus sigma? What is the probability that the strength is less than or equal to mu plus delta? Less than or equal to mu plus delta means, on the entire left area will come under this. What is the probability of, first question is, probability of x is less than or equal to mu plus sigma. This may be the question in the examination. If this is the question, what you do? The curve or some other information will be given along with the question. We will see some gate problems also little later. Probability of x means strength of the concrete. Probability of x, strength of the concrete, less than or equal to mu plus sigma. Mu value known, sigma is also known, area is also known. What is the probability? Up to this mu, the probability of occurrence is 0.5. And what is the probability of occurrence between mu and sigma? This is 0.3413. So 0.3413. So probability of occurring the result less than or equal to that will be equal to 0.8413. That means 84.13% of the results will lie below mu plus sigma. Will lie below mu plus sigma. That is the meaning of it, and this is how the numerical problems will be solved. That we will see little later. I will solve some of the numerical problems later. Okay. And most of you know, at this juncture, I want to mention one thing. Most of you know that FCK will be equal to F bar plus 1.65 times sigma. What is it called? Characteristic strength of the concrete. We will see little later, but anyway, at this juncture, let us discuss. FCK is the characteristic strength, which is equal to F bar minus 1.65 sigma. So what is the meaning of here? Meaning of here will be, meaning of this will be this area must be 5%. Characteristic strength means strength of the material below which not more than 5% of the test results are expected to fall. So corresponding to 5%, K value is 1.65 sigma. So F bar minus 1.65. In that way you can use for computing the characteristic strength of the concrete. I will discuss this little later. Now, okay, let's have a small problem. The problem based on that. Probability of strength falling below F bar minus sigma is below F bar minus sigma. So below F bar minus sigma means this is the curve and this is mu and this is nothing but sigma. So the area below this, what is the probability of this area? What is the probability of this area? Up to the center, it is 50%, 0.5. Up to the center, it is 50%. And what is this particular part? 0.3413, so that it is 15.87%. So in the examination, all the appropriate values will be given. Okay. Next, probability of strength exactly equal to average strength is. What is the strength of the cube exactly equal to the average value? That means the total area, that is nothing but 50%, 0.5, it is 50%. Or otherwise, probability of strength equal to more than F plus sigma 2 sigma, F plus 2 sigma. So for 2 sigma, associated value given 0.4772. This value will be given in the examination. Then only you can solve it. So it is 0.5 plus this one. So 97.72% of area will be covered if it is F bar plus 2 sigma. If it is F bar plus 2 sigma. So you know that characteristic strength, okay, characteristic strength of the concrete is strength of the concrete below which not more than 5% of the test results are expected to fall. That means area of this one is 5% and area of the remaining will be 95%. So the characteristic strength of the concrete means strength of the concrete below which not more than 5% of the test results are expected to fall. If this is the case, this value is nothing but 1.65 sigma. 1.65 sigma. So now what is FCK? This is F bar. F bar. What is FCK? FCK is nothing but this. FCK equal to what is the relation? F bar minus K into sigma. That K is now 1.65. 1.65 is corresponding to 5% probability. 1.65 is nothing but corresponding to 5% probability. So that's why it is nothing but given. Characteristic strength is defined not more than some percentage. If it is 5%, 1.65. Some percentage, it will be K. And in general, if the characteristic strength is defined as the strength below which not more than 50% of the test results are expected to fall. Okay, it's early we are discussing, we need to discuss originally characteristic strength. So what is the meaning of it? If the characteristic strength is defined as strength below which not more than 50% of the test results are expected to fall. That means this is not, the result should not lie here. When the results is not lie here, it is FCK according to this statement. According to this statement, this is FCK. But what is that value? That value itself is nothing but F bar. So what is FCK now? FCK is the same as F because sigma value is 0. Already I told you sigma value is 0 exactly at the middle point. Okay, I'll show you some numerical problems later so that it will be easy for you. And now we are at the grade of concrete. Concrete are different grades. We can call it in different groups. Ordinary concrete, which will be M10, 15, 20. Standard concrete, 25 to M55. High strength concrete, M60 to M80. So these are the three different groups: ordinary concrete, standard concrete, and high strength concrete. And of course, this M refers to the mix and number refers to the compressive strength at 28 days. Okay. So here in the minimum grade of concrete at different exposures. So several exposures are there: mild exposure, moderate exposure, severe exposure, very severe, extreme exposure. So the concrete structures may be constructed normally where the environment is not adverse. Environment is normal, then it is mild. And extreme means when it is like just like offshore structures. When the structures are constructed at the exposure of the sea water, that is extreme. And very severe means it is also near to that where lot of water currents, sea water currents will come and the structures constructed at those places. And severe where the buildings are constructed, buildings or any other structures constructed near to seashore so that the environment will affect. That is severe. And between mild and severe, it will be moderate. And of course, it has its own meaning in IS 456. And particularly for PCC, M15 is the minimum grade of concrete for moderate exposure. Just remember it, for moderate exposure, M15. And for RCC, even for mild exposure, the minimum grade of concrete is M20. So earlier in previous code, minimum grade is M15. Now the minimum grade of concrete to be used for RCC works is M20. It's an important point. And you can look at here the structures that are exposed to sea environment. These structures are not at the sea. It are not the offshore structures. These are near to the sea, so that the sea environment will come into picture, and minimum grade of concrete to be used as M30 grade of concrete. And you can see accordingly, if the condition is extreme condition, M40 grade of concrete is to be used. Now let us come to this characteristic strength. So far the entire statistical analysis, probability analysis is only for characterizing the strength of the concrete. So characteristic strength, strength of the concrete is different, average strength of the concrete is different, characteristic strength of the concrete is different. Characteristic strength of the concrete is the value of the strength of the material below which not more than 5% of the test results are expected to fall. For example, if you conduct exactly 100 compressive test results, compressive strength test results, only 5 results, this is 5%, only 5 results can be in the hatched area. And all the remaining strength values must be above that, then only this value is called the characteristic strength of concrete. So already I told you while drawing the diagram, these vertical ordinates are the compressive strengths, and this is the mean strength, and this is the characteristic strength. So this value characteristic strength value is depending on the percentage of the normal distribution curve. If the 5% is the area of the curve, the associated value is 1.65. K is 1.65. So the distance from the mean value to this will be 1.65 times of the standard deviation. So that's why FCK at this point equal to F bar minus 1.65 sigma, minus 1.65 sigma. For example, sometimes if the characteristic strength defined as we like, say for example, this is the percentage, say 25%. This is 25%. What is the characteristic strength for this? It is our own definition. This is the original definition given in IS 456 and we are following this. But for the examination purpose, assume that the characteristic strength will be a strength below which not more than 25% of the test results are expected to fall. And he may be given some k value equal to some say k1, maybe 1.23 or so. We do not know exact value. K will be equal to that. So what is this value? This value is nothing but now K1 multiplied by sigma. And this value is F bar. This is nothing but FCK. What is FCK? FCK will be equal to F bar minus this K1 multiplied by sigma. So knowing the values of F bar, knowing the value of sigma, and given the value of K1 in the problem, given K1 in the problem, you can find out FCK corresponding to the given statement, corresponding to the given statement. But the entire limit state method of design is completely based on the characteristic strength is only 5% base. So K will be equal to 1.65. But to test the basic concepts of this in the examination, it may be the question may be anything. Question may be anything. You need to understand the two terms. One is F bar. F bar lies always at the middle point. Another point is characteristic strength. Characteristic strength is the point of the deadline. Is the point of the deadline. So in as per IS 456, the deadline is 5% of the area. 5% of the area and associated constant is 1.65. So here deadline will be 25%. At that point, the strength is called the characteristic strength FCK. So accordingly, the relation between FCK, F and also the constant standard deviation. Okay. And total area of the distribution curve is always 1. So while calculating the characteristic strength, out of 100 cubes tested, 95 results must be more than FCK, more than FCK value. 95 results must be more than FCK value. So now, at the most 5 results, sometimes 0 results also, or 1 result, 2 result, or a maximum of 5 results may be less than the characteristic strength out of 100 test results. Okay, and this is the generalized term. This is only for the corresponding to 5%. If the percentage is different, K value is also different. So these are the notation. FCK characteristic strength of concrete, F bar average compressive strength of the concrete, sigma standard deviation, K is the constant corresponding to 5% probability. For 5% probability, this is the value. For some other probability, the values are again different. So now let us look at problem. Let us look at numerical problem. The compressive strength of test results of standard cube in MPA are 30, 20, 40, 36, 24. Only 5 results. For exact analysis, exact statistical analysis, minimum of 30 samples required. But here, for the sake of examination purpose, only 5 sample results are given here. What is the characteristic strength of the concrete? Here we need to find out the characteristic strength. So what is in general characteristic strength of the concrete? Characteristic strength of the concrete as per the code will be FCK will be equal to F bar minus 1.65 multiplied by sigma. That is the formula. Characteristic strength means it is only the definition given as per the code. But for the examination purpose, the questions may be with any of such deviation. Any of such deviation. So now let us have this. So with all these 5 values, you can compute F bar which is equal to 30 Newton per mm square. Average compressive strength of all the 5. Then sigma standard deviation. Compute the standard deviation. 1 by n minus 1 fi minus f bar whole square is the formula. So what you do? 30 first one is 30 minus 30 whole square. 30 minus 30 whole square. Second one 20 minus 30 whole square. Third one 40 minus 30 whole square. 36 minus 30 whole square. 24 minus 30 whole square. So that means deviation of all the values with reference to the mean, and 5 samples are there, it is 5 minus 1, and accordingly standard deviation is 8.25. Once the standard deviation is known, FCK is F bar minus this, substitute the value. So that means for the given set of data, the characteristic strength is 16.39 MPa. This may be the question in the examination. Some numerical values are given and what is the characteristic strength for the given data, and this may be the solution for it. Okay. You can also look another problem. Yeah. You can also look another problem. It is a cube strength results given. It is a frequency data given. In previous case, it is simply the 5 samples are given. But here the total number of samples that are tested is 20. But among these 20, 3 samples are with 28 Newton per mm square. 5 samples are 22 Newton per mm square. 4 samples are 21. Then 6 samples are 26 Newton per mm square strength. So here frequency distribution is also given, and accordingly x bar equal to sigma fi xi by sigma fi. Already you know the formula. Now to avoid confusion, we are now using x bar means average strength of the cube. So x bar is now you got 25 as per the substitution. Then standard deviation is 1 by n minus 1 sigma fi into xi minus x bar whole square. This is the formula. So these are the formulas not to remember now. These are the formulas already there in your mind. Only thing appropriate substitution and appropriate retrieval of the information is more important. So in that substitute 3 samples. First one is 28 minus average. 5 samples 22 minus 25, 4 samples 21 minus that, like that you calculate, and finally the standard deviation equal to 3.77. So by looking all these, you may get the knowledge, but you may not get the appropriate solution in a stipulated time. So what you do, for all these problems you have to use calculator and see that the values, how much time you are going to compute all these, and how much simplification that you can do. The time is more important in the examination. Sometimes you may be knowing the entire procedure and computation in the examination, but because of lack of practice, you may not get the final correct answer well within the time. So in such a case, okay. So you need to practice for calculator. With calculator, sigma equal to this, FCK equal to this formula as per the code, and accordingly 18.8 Newton per mm square is the characteristic strength for the given data. Characteristic strength for the given data. So for this data, the characteristic strength of the concrete will be 18.8 Newton per mm square. This may be the question. And sometimes the question may be, this is the question, another question. Here the question is over. One more question. What is the compressive strength? What is the compressive strength? What is the compressive strength? Less than F bar minus sigma. Compressive strength less than F bar minus sigma. You know, this is the curve and this is nothing but F bar, and here this is nothing but sigma. So what is this entire area? This entire area or this point is nothing but F bar minus sigma. F bar minus sigma. So in such a case, this ordinate will be F bar minus sigma. Earlier 1.65 used. What is 1.65? It is corresponding to 5% of area. So here area is something such that it is F bar minus sigma. F bar minus sigma. Now K is equal to 1. So what you do? Sum F1 equal to, here it is F1 equal to F bar already known. F bar is 25 minus standard deviation 3.77 and this is the value. But here don't use 1.65 because here some area such that the standard deviation is sigma only. Whereas here 5% is associated with 1.65 as the constant value. So sometimes the question may be like this or question may be in this way. Now let's go for characteristic load. So previously characteristic strength. So that means for materials, steel and also the concrete, we are giving more factor of safety by taking the lower limit of 5%. Whereas characteristic load as per IS 456 is defined as the value of the load which has 95% of probability not being exceeded during the life of structure. So that means when the load is such that this is called the characteristic load. In the same concept, earlier characteristic strength is this. Now it is called the characteristic average load. Earlier average stress. Now it is average load. So what is the limit for characteristic load? Limit for characteristic load is 95% of the load must be within this area, must be less than the characteristic load. So you can see that this is 95% of the area. The load that is acting on the structure must always be less than WCK. WCK refers to the characteristic strength of the load. Characteristic strength of the load. If the characteristic strength is defined here, the 95% of the times of the during life of the structure, load must be less than WCK only. At the most 5% of the times, the load may be above WCK. So that means here 95% of the probability. Now the relation between average load and characteristic load. So WCK will be equal to, you can use here WCK equal to average value of the load plus 1.65 times of sigma, 1.65 times of sigma. Earlier it is minus because we are moving towards left side. Now we are moving towards right side. So this will be plus. That means the factor of safety is introduced here by considering 95% of the load not exceeding the characteristic load. And these are the associated symbols just like characteristic strength. So that means here characteristic load is always more than the average load. Characteristic load is always more than the average load. Whereas characteristic strength is always less than the average load. Average, you can look at here. Characteristic strength, characteristic load is always more than the average load. Similarly, the characteristic strength, characteristic strength is always less than the average value. Is always less than the average value. So now, this is the relation for calculating the value of the characteristic load. Let us have one numerical problem associated with this. You can look at here. The structure is subjected to live loads of 42, 25, 38, 36, 44 kilonewton meter at different conditions. Characteristic load is, so what is the magnitude of the characteristic load based on the given set of the loads? So the structure is subjected to at one point of time 42 kilonewton per meter, another point of time 25, another condition 28, like that. These are the variable loads during certain period of time depending on the different conditions. And based on these values, what is the characteristic load? That's the question. The same formula, same thing, only thing is characteristic load is W bar plus K sigma. Here the only change is plus K sigma. And remaining procedure is same. W bar is average, which is 35, average of all. Now standard deviation, since the samples are less than 30, we are using 1 minus n1, n minus 1 here, and compute the square of the deviations under root, and accordingly you will get 8.37 kilonewton per meter as the standard deviation of the given loads. Once it is known, WCK is W plus K sigma, W plus K sigma, you will get 48.81. That means 48.81 is the characteristic load. What is the meaning of it? 95% of the times, 95% of the times, load acting on the structure must be less than 48.81 kilonewton per meter. That is the meaning of it. Characteristic load of 48.81 means 95% of the times, 95% of the probability, 95% of the time, the load must always be less than 48.81 kilonewton per meter. Then this is called the characteristic load, characteristic load. So this is how the computation of the characteristic strength and also characteristic load from the statistical analysis. Now, partial safety factors. Partial safety factors. Already I told you here factor of safety in limit state method is introduced both for the loads and also the materials. Both for the loads and also the materials, so that the uncertainty in the loads and uncertainty in the material strength will be taken care of. For materials, FD means design strength of material. Design strength of material is F by gamma M. F is nothing but characteristic strength of material. Characteristic strength of material, that may be in case of concrete FCK, or in case of steel, that will be equal to Fy. Fy is the characteristic strength of steel or yield stress of steel, and here it will be FCK. and gamma m partial safety factor appropriate to the material. So for concrete, the partial factor of safety is 1.5, and for this steel it is 1.15. 1.15. So you need to remember this. 1.5 is the partial factor of safety for concrete. 1.15 is the partial safety factor for the steel. Similarly for the loads. So you know what is going to happen here. The stress is reduced by imposing the partial factor of safety. So FD means F divided by gamma m. F divided by gamma. That means the value is reduced here. Whereas in case of loads, the design load is multiplied with the factor. Multiplied with the factor. So the design load is always more. Design load is always more. FD equal to gamma F into F. So FD is design load, gamma F partial factor of safety, F is the characteristic load. And here gamma F value, in general we can consider it is 1.5, but for different types of loads and different types of limit states, the values are different. So remember here to introduce, to provide safety for the materials, the character strength of material is reduced by imposing the factor of safety. And similarly, for providing the factor of safety onto the materials, the loads are multiplied with some value so that ultimate loads are considered. So in the illustrated, ultimate loads are considered from the safety point of view, and material strengths are considered from the serviceability point of view, and both will serve for the purpose. And you can look at here, the value of partial safety factor for material strength should account for possibility of deviation of the strength of a material, accuracy of calculation procedure, risk to life and economic consequences. Because of all these reasons, the partial factor of safety is introduced, and the strength reduces accordingly. Then the value of partial factor of safety for the loads is accounted for unusual increase in loads. Sometimes loads may be more than the characteristic values. So that's why we are using